All right, thanks, Tom. Yeah, and thanks everybody for having me. Pleasure to be here downstairs at my house. So I was saying I just got in town from Clemson, South Carolina, visiting my folks. Um, but yeah, happy to be here. Thanks for the introduction, Tom. This is a unique project that Tom alluded to that I've got to work on compared to other types of research studies that I do and others do, right, in terms of going after National Science Foundation funding or USDA or the like. This is was and still is a unique collaboration between the Nature Conservancy, as Tom mentioned. They've had an active role in at the Virginia Beach, largely because of City Councilwoman Barbara Henley, who's been a city councilwoman for quite some time and very, very interested in kind of nature-based solutions. Really a very strong person that's kind of pushed and helped shepherd a lot of different projects along in the city, including collaborating with the Nature Conservancy and Brian Van Erden there. And so, yeah, it was a unique collaboration because it's with the NGO Nature Conservancy in a locality, Virginia Beach, to fund what now has become two phases of the work. So, yeah, I've already mentioned Brian Van Erden. He's been a valuable collaborator in other projects as well. Like the Great Dismal Swamp and some other areas, but particularly in this project, the Nature Conservancy. And then at Virginia Tech, Yang Xiao, who is, I think, got his PhD along with Tom with the same advisor at UNC, as well as, and he's in geography in my College of Natural Resources. And then David Sample, who's actually at the ARAC in Virginia Beach, but he's part of the Biological Systems Engineering Department at Virginia Tech. I'm not going to go into it now today because we want to focus on the title at hand. But I started getting interested in thinking about managing forest for water resources, actually for the flip side of what we're going to talk about today. And it started in Florida, actually thinking about places where we have rural lands. A lot of times we have industrial forestry operations or relic forestry operations, and places where we value groundwater recharge to support minimum flows and levels in our groundwater aquifers and stream flow. And so that project was on the ground using a lot of sensors from soil moisture sensors to water level sensors, trying to get at kind of stand level evapotranspiration, which I'll define here in a bit. But thinking about managing forest to yield more water, thinning, prescribed fire, longleaf pine restoration, things that actually decreased the amount of forest cover and mimicked kind of stands that historically what they would have looked like before timber production or fire prevention or suppression, I should say. Thinking about groundwater recharge. And actually, that's how this project got started. Brian Van Erden, we were talking about it and thinking about doing some similar in other parts of Virginia, thinking about managing forests for more water to supply for like ephemeral wetlands. And he said, well, I'm in Virginia Beach and we're thinking about places where we have too much water. Can we think about forest in the flip side? And that's what we're going to talk about today. Of course, and the reason Brian and others have tried to work with municipalities and other stakeholders to preserve forest, conserve forest, or even restore forests is because we all value a lot of these ecosystem services that you see. That I don't need to go into all the ones that we see, but they are very much tied to water resources. And I just alluded to thinking about places where we don't have flooding issues, but we have issues for groundwater recharge. We value forest for water supply because that's high quality in terms of water quality for groundwater recharge. And we can think about managing forest for more water potentially in those sorts of locations and needs. However, we also think about them in the context of today, in today's talk, in terms of flood control. So what I'm going to do is I'm just going to give you, just to make sure we're all on the same page, a very high level, as is most of the talk. I'm not going to go very much detailed in any particular methodology or in the really fine-grained results. It's kind of just showing you the arc of the two projects and what we've found so far and where we're going. But before I do that, I'd like to just get us all up to speed on, and again, at a very high level about how kind of forests interact with water resources. They capture water, of course, then they store it and they use it. And we can think about the landscape features and the forest structure features that kind of regulate all of these, right? In terms of for storing what, capturing and storing water during any given storm event, and then using water, right? So here's just a simple diagram to kind of walk through first storages, because we focused on both storages, the ability of forests to kind of grab and hold that water, as well as then use that water. So first the storages, they're canopies, they're umbrellas. We think about it from interception in terms of one place they can hold water, surface water, depressions within, and usually kind of smaller wetlands that are embedded in otherwise forest. We can think about them grabbing and holding that water. And of course, soil infiltration going through the vadose or unsaturated zone, staying there or infiltrating all the way to the water table. And of course, the difference of that is what's left over is runoff, right? I think everybody values this. I think we value this from a runoff reduction perspective, thinking about individual street trees, right? And maybe the little bit of soil around them to larger forest patches. But we did set out to quantify the potential for storage across forest and other land use features in the city for more of a quantitative comparison. But what I think I've already alluded to, and a thing that maybe gets less emphasis in a process is the ability of forest and any other landscape to return, or the potential, I should say, to return that water back to the atmosphere through evapotranspiration, right? Which is the combination of direct transpiration from any type of vegetation cover, open water, physical evaporation from any standing water. So you can see that little pond decreasing from what it was following a storm event, and then any water that can that's close enough to the surface for soil water evaporation. Collectively, it's evapotranspiration, and it's an atmospheric flux back up, and they can vary across regions. I'll show you that in a bit. But the point I'm trying to make here is we can think about the ability of different land cover features, from retention ponds to naturally embedded wetlands to forest soils, in terms of ability to capture water in any given storm event. But between storm events, those antecedent conditions or preceding conditions and largely evapotranspiration can help regulate the storage capacity for the next round, right? So you could have the same kind of situation in terms of depressional storage and soil permeability, but the idea here is if you have more evapotranspiration in between rain events, then that sets up more storage capacity, depleting water in the vadose zone, lowering the water table, decreasing water in depressions, so on and so forth. So, you know, this is a definite emphasis of the project. So we can think about these, just some eye candy to think about some embedded wetlands that and depressions that hold surface water perennially or intermittently, or maybe even ephemerally just during storm events, and they can vary in terms of what they look like. We can think about them from a landscape view, right? You can almost squint and probably see some of these surface water depressional features here from this image. But as Tom and I were just mentioning and discussing, we have LiDAR now to really get at high resolution topographic information. And this is not my image, but I thought it was kind of cool because it put a forest next to some urban area, and you can see some depressional storage. But we've used high resolution LiDAR in other places, particularly the Delmarva Peninsula, and some work there, really refining the ability and workflow and programming to get at water storage capacity of small to big depressions. And so we kind of work through that workflow in that project with a completely different focus and implication, but nonetheless, think about taking what is increasingly available high resolution LiDAR to get at depressional water storage capacity. How much water can a depression hold before it spills over? For soils, I probably don't need to go through this in much detail, but there's characteristics of soils that mean they are better or worse at infiltrating and storing water, from permeability showing here, where we have high permeability, and the same thing goes for porosity. And so we need to kind of think about that, regardless of vegetation cover, in terms of different soil infiltration capacities. And of course, that's been thought about for quite some time and already included and represented in plenty of stormwater and other hydrologic models. Another aspect of that potential for that subsurface to store water is not just the soil properties, but how high that water table is. So this kind of rough sketch on the right here, that green top line is supposed to represent the land surface. That blue rectangle on the top of that is supposed to represent the superficial aquifer, or the water table, I should say. And the idea is, regardless of soil type, a low-lying area with a high water table or a high water table condition before a storm event means less room for any infiltration, right? And maybe you've heard of saturation, excess flow, or the variable source area concepts. But regardless, either differences across locations, as I'm showing here, or I could show it differences between different storm events and antecedent conditions. So if you have a high water table because of a lot of preceding rain, before next round of rain, you're going to get a lot less infiltration and more runoff. But if you kind of think about place and evapotranspiration in that context, a location that has more evapotranspiration, a landscape that does in between storm events, could potentially not just reduce soil moisture, but also lower that water table, again, replenishing that storage, that water storage capacity. And then last, they grab that water, they store it in their soils and the aquifer and any kind of surface water depressions. But again, emphasizing this evapotranspiration to replenish, and the extent, the timing, and the magnitude of that evapotranspiration really has an effect on pre-storm conditions in between storm events, in terms of kind of setting the stage for how much storage capacity there is. And just to kind of sit on ET for a second more, just to emphasize that there's regional differences, which I think is not surprising. This is an older figure from Sanford and Selnick, looking at the estimated fraction of precipitation lost to evapotranspiration. Excuse me. And so, you could get in the Pacific Northwest, we think of it as a very wet climate. I think most people think of it because it rains all the time, but it also has really low evapotranspiration rates, right? Cloudy all the time. Cool. And so maybe 20% of incoming precipitation is removed and goes back to the atmosphere. And of course, what's left is what recharges our aquifers, goes in the soil water, but also can become runoff, particularly in urban areas. We can zoom in on the golden corner of South Carolina, where I just was, and we can see we might be creeping up to maybe 40%. We can think about Gainesville and the University of Florida, where I used to sit, 70 to even 90% of the incoming precipitation, which I think is a surprise to some folks, that 70% in some locations and even more of all the annual rainfall just is returned back to the atmosphere. And what's left then is essentially landscape wetness, and depending on the features, if it's a flat area like Florida, even it might not be that much, it sits around because it's flat, right? Whereas in the golden corner of South Carolina, we're well drained, and other than reservoirs in our river systems, right? But also in urban areas, that means more water to fill up our locations of storage capacity and subsequently create runoff. Where you all are sitting, or some of you anyway, might be 60 to 50%, and then in Blacksburg, a little bit less because of climate drivers, clearly, right? The things that drive ET, evapotranspiration, in terms of the demand, and this is an idea I'm going to come back to, are things like solar radiation, relative humidity, and wind, right? And so it makes sense why we have these big kind of regional differences in terms of the magnitude of evapotranspiration water just returning back to the atmosphere. These aren't necessarily the best of images, but the point here is, even within a region, it varies based off of land cover. This is an extreme version, and don't even pay attention to the percentages, but really kind of the change in the allocation of incoming precipitation. right? And so this landscape might, in a natural setting, might be, maybe it's one of those regions that up to 40% of incoming precipitation goes back out to the atmosphere as evapotranspiration. But in that same landscape, same annual rainfall, if we essentially seal that environment from any water availability, right? We don't, yes, we don't have the vegetation, we don't have the straws tapping into it. We also don't have exposed soil for soil water evaporation. And so we get a decrease, and I would argue probably more than what's represented here in that percentage from 40 to 30%. And of course, we also get less infiltration, which I think is a more obvious issue with increased impervious cover, but the take home is both of those things increase runoff. And to go back to some of our Florida work, working specifically and directly in forest, even forest can vary in their evapotranspiration. So some of our sites there were uneven, widely spaced longleaf pine with very much kind of exposed understory, low canopy coverage, and that particular forest stand, it might be 60%, 70% of incoming precipitation back out to ET. Whereas we had an experimental stand right next to that where it was old relic, high density timber stands, and they were up to 90%. So even within a specific land cover, like forest, or from low residential to high residential urban cover, with the same climate drivers, you can get quite big differences in evapotranspiration, right? And that can have big implications for water yield, or in this case, in our focus, runoff. And just to kind of hit it home, this is from iTree, which is work gone on in the Midwest. It's kind of gotten popular in terms of a model to kind of think about green space and the value of urban trees. So we kind of, these two extremes, right, where we've with the same climate drivers, we've increased runoff and the amount of water that sits on the land surface a lot. And again, not just because it can't go into infiltration, but also we don't have the straws in the system. And this is not a new idea. People have recognized this. We have an urban forestry program within my department, thinking about the various aspects of urban forest and urban trees, right? From shading, microclimate regulation, habitat, maybe in terms of individual trees that could be subject, but nonetheless, you know, a lot of different ecosystem services, carbon storage, but also representing their value in terms of canopy storage and rooting, helping to establish infiltration. But, and I should say, the city of Virginia Beach has definitely embraced this. This is from their sea level rise report a couple of years ago, which is really guiding a lot of the work in Virginia Beach in terms of mitigating and adapting to sea level rise on one end, but also increased urban flooding and runoff from impervious surfaces. And there's adapted structures, prepared communities, engineered defenses, but they're recognizing that there's a portfolio of actions for solutions of flood risk. And so I've, in green, circled natural mitigations from SAV to, submerged aquatic vegetation, oyster reefs, you name it, kind of right on the coast, but also things within more inland, kind of flanking the waterways in the city. And that's that circle on the top, thinking about urban forest. And really kind of thinking beyond just street trees, right? That's what we're seeing here on the right, where we see individual trees in a low residential neighborhood, low intensity neighborhood. But the city and others, but I think the city is particularly fortunate, have pretty big forested tracts, right? And so kind of thinking about not just individual street trees, but the roles of forested patches, where they are in terms of runoff features in adjacency to flood-prone areas and infrastructure, thinking about the value of these forested patches. And indeed, the city is fortunate enough to have about 30% of its area covered in forest, just shy of 30%. And I think that's a lot of forest for the city of Virginia Beach and localities such as that. And you can see that there's, so on this figure, is showing that 30%, but is also distinguishing between forested that are protected, and that's a pretty loose word, but they might be under conservation easements or owned by certain NGOs, the city itself, in terms of public lands. But the burgundy or maroon, whatever that color may be, are unprotected that could go to some other land use. And we can see, if anybody's familiar with Virginia Beach, that there's more in the southern end below what they call the green belt. Most of the development historically has been in the north end, but it is creeping down. So that kind of led the idea. That's kind of a good, trying to set the stage for our project that was specifically in Virginia Beach. But I think the approach, findings, and implications extend to other flood-prone municipalities, particularly ones low-lying with increased impervious cover. And then, of course, on the other side, the coastal squeeze with sea level rise. So we had two phases. Phase one was to essentially take a first look. It wasn't much funding to do any kind of on-the-ground research, and nor would over an area like this could we go out and instrument to measure various different things, from water table heights to soil moisture loss and gain to evapotranspiration. Imagine putting a lot of eddy covariance towers, of those of you familiar with that, which some would argue is the gold standard in measuring evapotranspiration, but it has a limited inference space, less than a square mile, and they're about $100,000 a piece. So what we were interested in is to get a landscape view of these flood risk kind of services, both the ability of different land covers to store water and that water removal. And so it was not just in forest, but other land cover types as well. And then we kind of wanted to make it more actionable science, particularly for the stakeholders that we're working with, and to not let the data sit, on somebody's computer at Virginia Tech or in just a publication, but to try to get it to the ones that are making decisions in a tool that's available and pretty easy to use to kind of build from the data that we gathered and processed. So that was phase one, to kind of give a first look and at the potential, and I'll come back to that, for different flood prevention or mitigation services. And then phase two, always in the background of when we even started phase one, was saying, okay, to really get the role of forest more formally incorporated as like on BMP clearinghouses, best management practices for stormwater mitigation. And to do that, we can't just sit at an annual scale and say, well, this is the annual potential for water storage in soils, or ET, but more thinking about understanding at a smaller scale, smaller temporal scale as well, what does that mean for changes in actual runoff, right? Because in phase one, we're looking at the potential for water to get stored and removed, but not directly quantifying runoff. But to formally incorporate forest and other land use and to understand their potential role in stormwater reduction, we need to incorporate them better in stormwater models. And of course, if we can get there, and that's where we're kind of are now, we can model scenarios of forest loss or restoration to quantify changes in runoff and begin to play games, if you will, of identifying priority forested patches that have an outsized role potentially in runoff reduction because of certain features of that particular forest stand, such as canopy cover or soil type, but also its position in the landscape relative to flood-prone areas. All right, so to do both, and really to start with phase one, we want to get at flood reduction potential. And this is what I mean by potential. Nothing about actual runoff rates in phase one, just looking at kind of estimates of potential surface storage, potential soil water storage, and potential for that water to be removed and returned back to the atmosphere and the evapotranspiration. So we had to go out and think about the data that are available, because again, we're taking a landscape view And so we needed data that were already available to kind of piece this together. And for surface storage, as I already alluded to, it was LiDAR. We have good LiDAR in the very good LiDAR in the city that was flown for another project. This high resolution LiDAR. This is not the, if I zoomed in, you could see different, distinguish between the layers a little, or the color ramp of the layer, I should say. This is essentially depression, and in terms of millimeters of how much water can be held in different depressions across the city. And you can kind of see some pop out. And again, what we did for that was we used LiDAR and we said, how much can that depression hold in terms of millimeters spread out over this area before it spills over? That doesn't mean that it is, right? We're not quantifying actual water storage yesterday or tomorrow. It's the potential of a depression to hold water, okay? Similarly, we did the same thing for soil storage. Some of you might be familiar with Surgo, which is a very available and commonly used data set, geospatial data set for soil types. And it tells you things such as hydraulic conductivity, porosity, things that we can get at water storage, potential in the soil water, again, shown kind of per unit area as millimeters here. But we also need to bring in that idea of, regardless of soil type, if your water table is shallow, you're going to have less room. And again, I'm kind of skipping over the method details here, but the data that we used was soil type, soil permeability, if you had impervious cover or not, and the extent of that, as well as depth to water table that we used by stitching together, I think about 15 groundwater wells managed by the USGS, looking at kind of mean annual water table. So we have mean annual water table. We have something about porosity, if there's how much percent impervious cover, and we can get at the potential for those pores to hold water, again, per unit area as millimeters. And we can see there's differences across the city. So those were a little bit more straightforward. We had plenty of experience estimating surface storage capacity using available LiDAR in previous work. The soil storage is pretty straightforward, but when it came to evapotranspiration, which was really the emphasis, or one of the major emphasis of the work, to kind of get that better represented, and I think that I'll highlight that a little bit more when the need for that in phase 2. We had to think about it a little bit more closely and kind of search and comb for available data sets to be able to get evapotranspiration rates, which is one of the hardest measurements to make, even using field techniques, right? Because you're looking at water vapor returning back to the atmosphere, but at a landscape view, maybe even a little bit more challenging. But luckily, and it's been around for some time, we've had satellites, in this case Landsat, cruising the Earth for over 20 years, every 16 days. And about a decade ago or more, folks primarily for agriculture land uses developed a method that I'm not detailing here, but for those interested, is called the metric model, that uses Landsat imagery, particularly thermal data, to get at evapotranspiration. So evapotranspiration is like you perspiring on your skin, right? It cools your body off because it's a latent heat flux, or an endothermic reaction, right? So the more evaporation you have going, the more of solar radiation energy is going to fuel that process versus changing surface temperature, right? And of course, if we put a sweatsuit on or we pave an area, we are decreasing that, our ability to perspire or evapotranspire, and so the land surface gets warmer. And so depending on impervious cover to other covers, natural covers in terms of the big extreme, but even differences in canopy structure can yield different evapotranspiration rates, and it can be reflected in surface temperatures collected by satellite imagery. Of course, it's not a direct measure of evapotranspiration. There's been quite some work, and not by our group, to kind of calibrate those models to use that imagery data along with other information to estimate spatially evapotranspiration. And here's an image from Colorado State University. But Landsat comes out with a 30-meter resolution data set, and therefore so does the metric model. by 30 meters, 30 meters by 30 meters on a square, we get one number every time that satellite flies around for evapotranspiration. Now, of course, we can't leave it there, right? We have 20 years of data. We have cloudy days. We have not very good or other reasons of bad imagery. So it takes a lot of data processing and other methods I'm not going to go into to get a reliable data set for actual evapotranspiration rates. And so working with Yang Xiao primarily on this and his student, who's now with DOE, developing or using the data at hand to develop time series or evapotranspiration rates every 30 meters by 30 meters across the city of Virginia Beach. And so that's what these data look like. And you can see we have clear differences across the city in terms of the potential for a total evapotranspiration in terms of per unit area, depth of water being returned back to the atmosphere. So now we have these three kind of data sets stitched together to extract with high, and we actually have very, very good land use data that was done by the University of New Hampshire, I believe, for a different study. But to now say for each individual different land use or our pixel, what are these potential for surface storage, soil water storage, as well as water removal via evapotranspiration. So, I mean, this is very high level findings, pretty coarse bar graphs, even a pie chart here in a second, but just kind of the take homes, right? So for water storage, we're looking at soil water storage on the x-axis. We put it in inches in this case for the city of Virginia Beach and other stakeholders. And for this sake, and this kind of simplified view, we have urban open space, urban high intensity, we have upland forest, and we have wetland forest or swamps. But we have this diced up a lot more finer in terms of land use categories. We have medium intensity, low intensity in terms of urban. We have different types of upland forest, and the same thing goes for wetland forest. And we also have ag that I'm not showing here as well. But the take home from this graph is that for soil water storage, of course, we don't have much in high intensity. Those are low numbers. That should make sense. That seal in terms of impervious cover, not letting that soil, regardless of its type, infiltrate any water. Whereas open space, not the forest, but any kind of open space, parks, you name it, really high values, which makes sense. Those open spaces tend to be upland areas, water tables a little bit deeper, plenty of places for infiltration. We get similar numbers for upland forest, which makes sense, right? Upland forest by definition are, deeper water table environments, drier soils essentially. Whereas wetland forest, yeah, we have soil, exposed soil ready for infiltration. We have roots kind of helping that with that a little bit, but the water table for a wetland by definition is higher, and if not, sometimes above the water surface that you're splashing in. So less for water storage, but still more than urban high intensity. If we look at depressional water storage, we kind of get the same view, right? We kind of get a little bit more in urban high intensity than soil water storage, maybe because of retention ponds, but look at the value for urban space, upland forest, again, dwarfing that of urban, and wetland forest kind of somewhere in between. So I'll use this to really stress the difference between open space and high intensity urban in terms of the potential to store water. Now, this is just storing water. And I want to think about or highlight the value of open space is really good at infiltrating water. But in terms of water removal via evapotranspiration, we'll see it's going to be lower. I'm just going to go ahead and jump to that kind of take home, meaning that might be a place that we can value the surface, the storage capacity, but we could also think about places for forest restoration to increase evapotranspiration. And what I mean by that is this graph, right? So now we have the urban open space sitting at, an annual estimated rate of evapotranspiration close to 30 inches. Urban is hardly 10. Upland forest is more than both, as you'd expect, the trees, right? And we can think about that urban space. We could kind of get a little jump up with forest restoration. But what really stands out are wetland forest, over 3 times the rate of urban high intensity. Now, wetland forest is a pretty broad category of type of forest, from maple stands to cypress flanking waterways, and the list goes on, right? And we can dice that up in finer categories. But the point is, as characterized by the NLCD, wetland forests are 20% of the total area in Virginia Beach. And what I mean by that is, I said that 30% of the total land area in Virginia Beach is forest. Most of that, 20 of those 30, are characterized as wetland forest. And if we take the total amount of ET as a plane leaving the surface of Virginia Beach, all pixels combined, 40% of that total would be coming from wetland forest. So outsized role in terms of their coverage, which is still large, 20% of the land area, but double in terms of their contribution to water pumping, in terms of water removal back to the atmosphere. So they are a dominant land cover and the dominant forest type within City of Virginia Beach, but nonetheless still perform disproportionately higher in terms of their water removal. And if we add those to upland forests, remember I said that we were just shy of 30%. So forests cover 29% of the land area. And here's this pie chart, but almost 50% of the water lost through evapotranspiration. And now I've got them diced up compared to the total from urban. So urban is the dominant land cover, but only 20% of the total pie comes from urban, whereas and we can see ag and other, whereas we see forest almost half the pie in terms of that total amount of water, even though they're 30% of the land area. Now, with that information, we can start to play scenarios, and probably not reasonable scenarios in this case, but this would be saying, if I took out all of the burgundy on the left, that unprotected forest, and I replaced it with different land uses, knowing their rates, what would be the change or the loss in total amount of evapotranspiration that occurred in that what was forested land? And we can see, as you might expect, big losses in ET, bigger for high intensity and less for agriculture, which should make sense, but still, nonetheless, forest using more water than agriculture. So we can start to play these games. We can do other things, and we just not shown here. We can think about different scenarios of sea level rise, right? Grabbing essentially that wetland forest in a lot of cases, and a kind of a double whammy in terms of sea level rise and that contribution to runoff. But then at the same time, the loss of what were freshwater swamps, and now, and you've probably heard of ghost forest. So we've done that and played different games of different sea level rise scenarios to also look at changes in evapotranspiration rates. And as I mentioned, we didn't want to kind of leave it there. We wanted to kind of get it in the hands of folks that might be using it. So this is something that Yang Xiao led primarily, using those data that sit on a server, but that in real time can be accessed by users as a publicly available website that can be accessed by users in various different ways to toggle through different categories or layers, I should say, and even extract information. So here, just because it's, it highlights the resolution of the information here. Here is our DEM, our digital elevation model, as one of the layers, but we have layers for, of course, just imagery, our evapotranspiration numbers, storages in terms of surface water and soil, and you can zoom in and out and toggle. But there's also ways, and I'll show this in a second, to draw a polygon of interest. Maybe I'm interested in this particular area, and extract some information, or even drainage based, which I think is pretty cool, where you can plop a point in anywhere. Maybe it's an area that someone is worried about or concerned with flood issues, and it will delineate the local drainage area or watershed that drains to that point and extract, well, what's in that watershed in terms of forest cover, urban cover, and their relative roles in terms of storage and evapotranspiration. So just to kind of illustrate it for evapotranspiration, here's that same website user that, again, is publicly available. You could toggle on. Of course, we're looking at imagery. Of course, wherever your cursor is, you're getting information for potential sea level rise scenarios, as those top two. Surface water, or excuse me, soil water storage, that's that third one on the top right. That layer of evapotranspiration, layer for depressional water storage, the layer for our interpolated water table depth, as well as that DEM. And if I toggle between this one and evapotranspiration, first of all, you see the resolution of the data now. That's at 30 meter by 30 meters square, but you can also see big differences where the blues are hot spots, or cool spots, I should say, for evapotranspiration. And they clearly track with land use, right? I mean, you can see this waterway in the middle, and you can see its surrounding wetland, but you can even go up to little individual forest patches and clearly see higher evapotranspiration rates as you toggle back and forth. So again, I also said that we were able to provide in real-time way of extracting information. So you can draw a polygon, as this screenshot shows. It'll throw out and give to you tabulated data for forest cover, urban cover, ag, grassland cover. Then it'll show you the ET distribution. So in this case, the land cover distribution, 60% of this polygon, or this shape, is about 62% is forest cover, but that forest contributes 80% of the ET that comes from this polygon. And 63% of soil water storage and 50-something% of depressional water storage. And you can see the numbers for the other land use. And of course, we can throw out graphs as well. So it's a really cool tool for folks to just play around with for outreach and to kind of help inform the public of the roles of forest in terms of this particular ecosystem service, but also stakeholders to maybe use it more operationally. I'm not showing it here, but again, that other drainage base analysis, that second blue on the top right, if you click that, is going to say drop a point. You drop a point, and it will use the available DEM and a watershed delineation routine to delineate the area that drains to that point, and then extract similar information for that drainage area that I'm showing here. So that's pretty cool, and a nifty tool that's still available. Now, the take home from phase one, take homes, I should say, was, we gave some data and that tool to quantify flood reduction services to kind of help inform actions in the city and others. And I will say that it did help, as not as big a player as the sea level rise report, but it did help in some substantial money for forest conservation in the city. That happened a year or two ago. Upland forest in the city, in this domain, or the coverage is low, so the ET contribution is low, but nonetheless, they're areas and might be strategic areas to look at. Wetland forests are 20% of the area, the majority of the forest type, but 40% of the cumulative ET. The value of green space for all services, right? Particularly that storage, thinking about those might be prime areas for restoration to get some canopy cover and some straws in the system. Of course, urbanization decreases infiltration and storage services, but also reduces ET. And if we can play games with the loss of unprotected forests. But as I suggested early on, phase one supports the importance of forest conservation. However, to really inform stormwater planning and to, with the goal of better representing and formally incorporating forest covers and other green space into planning efforts, requires not just the data I've shown, but stormwater models to then say, well, what does that mean for runoff for different storm events and storm event characteristics? So that led us to phase two, which we're in the midst of wrapping up now. So all the results are preliminary that I'm getting ready to show in the works, but we're getting close. And the idea was first to quantify reduction rates for different storm events and estimate changes in runoff rates with forest loss. So now estimate losses of annual evapotranspiration or annual surface water storage, but actual runoff, well, modeled runoff rates for a given storm event with and without forest. So our approach was to use a model that the city uses, as calibrated, and that many other municipalities have used from the EPA, which is the Stormwater Management Model, or SWIM. It's a really good model, and very useful operationally. I can't stress that enough, for design storms and to size culverts and to size detention ponds. However, it only uses, most often in almost all applications, one evapotranspiration spread out over a daily evapotranspiration, spread out over a whole model domain, right? One rate. Furthermore, it's based off of potential ET. So how hot is it? What's the wind? What's the relative humidity? It's all the potential evapotranspiration. That's the demand sitting in the atmosphere. How much water vapor does that atmosphere want, that parcel layer want on that given day? If it's hot or if it's cold or if it's windy or not, if it's humid or not, more or less demand for water vapor. But how much actually meets that demand and how close you get to that demand is, well, how much water is available in your soil pores, right? But also vegetation cover versus other land covers. We've already emphasized that clearly there are differences in different land covers. So one of our goals was to, and I'll show this in a second, was to get where it was easier for users to better represent land cover differences in evapotranspiration rates, and not apply just one rate and not just one that's based off of climatic demand. Now, at the same time, simulations for SWIM are often said, okay, for a given storm event, a 25-year storm event, these are our antecedent conditions. These are initial conditions. This is right before the storm, run it. Which is great to see, well, for given conditions, how much runoff is going to be generated for a given storm event in a given location to say we need our culvert bigger. Very much appropriate and right on to inform those type of efforts. Either of these things, right? Because we don't care about differences in ET in a given storm event. There's not much anywhere going on, and it's not going to really matter for an individual storm event. But when it does play into fact, is setting the stage for any given storm event. Now, again, if I'm sizing a culvert or a detention pond, I'm interested in, for a given land setting and a given initial condition, here's a storm event, how much runoff is generated. But if I'm wanting to understand or get a handle on how do land cover differences actually change those initial conditions, i.e. the storage capacity leading into that rain event, well, we need to, again, better represent ET, but also model continuously, let's say a year or something like that, so that we know what goes on between storm events and what they mean for those storm events. And I've already emphasized this, while we first need to, if we're interested in land cover effects on preceding storm conditions, well, clearly we need to represent ET differences better for individual land uses and pixels. And so our approach was to just do that. Refine the ability and get into the code of SWIM, the program, to actually allow us to get different ET rates for different subcatchments, and that's how it models. To get it, so we first did that, and then we said, well, now we want to inform what those rates are. We have our ET data from our satellite imagery, right? But that might be 10 different rates that we got in a given year versus last year and years before, over 20 years, right? But we need to estimate daily evapotranspiration. And so an important point is that the y-axis on this graph on the bottom is the ratio of ET, an estimated actual rate, relative to the demand in the atmosphere. And theoretically, the maximum should be 1, but of course, PET is just an estimate with a mathematical model in of itself. But you can see that there's seasonality to these different land uses. The star for this given set of pixels are wetland forest, the open green circle are upland forest, and that cross is urban. You can see there's a seasonal signature with dormancy and then the growing season. And you can see that our forests approach 1. That means that pretty much if you have whatever that rate of PET is in the summer months, it's meeting that rate. It's meeting that demand, right? It has straws accessing soil moisture in the water table. We see it blip up a little bit from urban, but clearly big differences of 20%. And so if we have this curve for each pixel, which we do, we can fit a model to it. Then for each pixel on any given day that we have a PET, which is just informed by meteorological data, we can say, well, on that given day, we have a prediction of what the ratio is, and we can estimate out ET, or actual water vapor estimates thereof, leaving that particular pixel on any Julian day. And so that's what we've done. We've derived, so we refine the model to handle different ET rates that we apply on a given day. And we've developed essentially an ET time series from our original satellite imagery and climate data as inputs. Maybe to put a map on that, on the right here we have that same ratio of ET to PET broken out by subcatchments. The darker blue is getting closer to 1. The light colors are getting closer to 0. We can highlight one of those zeros and we can see it's that individual curve in terms of kind of similar to the one on the left for those crosses, maybe getting to 30% in the growing season, whereas we can see this area maybe is mimicking more like an upland or wetland forest where you get bigger differences. And we can kind of fit models to this to allow us to now give this particular model domain different ETs rates to apply before storms, during storms, and after storms. And again, that was our approach, not just to do that, but to run swim continuously and for wet and dry years to represent pre-storm conditions, and mainly thinking about, well, how much storage is in that depression? How much storage is in that soil moisture profile? And thus how well the influence of ET leading up to any given storm event on replenishing that storage capacity, going way back to that original conceptual diagram. We, not modeling the whole city, we work on are working on 2 study drainage basins, and I know I'm almost out of time, run scenarios of forest loss. Here's one drainage basin. It's a mixed land cover, but still a lot of forest. It's a place where development is estimated to, or guessed to happen. And so it was a good place for us to represent different land cover types, role and runoff reduction, and then to play the game of forest loss. And here are these 2 subcatchments with layers on runoff difference. So this is the delta in runoff with a negative number, meaning you decrease runoff. And this is just saying don't even worry about forest or not forest, but for given land cover or land use types, if we modeled it with the original type of ET representation versus better representing ET, we now get spatial differences in runoff, and we get reductions in runoff, just saying we're doing a better job of representing evapotranspiration, even for current conditions in our model simulations. Almost done. And here's just a box plot. Again, pretty coarse in terms of the results here, but the runoff is on the x-axis and different model simulations over a whole year. And we did this for a wet year and a dry year and a median year in terms of annual rainfall. The 2 on the left are current conditions. The bar graph on the left of that dashed area is the current model without representing ET. And we can clearly see even under current conditions, representing ET reduces the median and the distribution. And if we just say, well, what if of the forest in that given case study watershed, what if we lost 15% of that existing forest? So that's kind of a modest reduction, but nonetheless, we see that there's drastic changes in runoff, increasing with that arrow to note that compared to current conditions with either model, but particularly with the ET-based model. So last slide, I want to emphasize first what this has been a pleasure to work on, a very collaborative project with Virginia Beach, that locality, the Nature Conservancy, but we've also had a larger kind of forest conservation working group that included folks from the Fish and Wildlife Service, the NGO Lynn Haven River Now, Department of DOF, and others. We've hopefully provided just a first look and information and tools to kind of just broadly kind of put another feather in the cap for forest conservation. And hopefully, as we go forward with this swim refining and stormwater modeling, more information on restoration management and more formal incorporation into stormwater planning.